Hello everybody. In this video, we will be discussing topicity and stereoisomerism or prochirality. The atoms or groups in a molecule which are in isolation looks the same or mirror image to each other are usually referred to as homomorphic atoms or ligands or group. See this example. Here it is propane. These two hydrogens are homomorphic atoms, and these two methyl group also homomorphic, and it is homomorphic groups because they are in isolation, are identical and superimposable to each other. See, for example, this hydrogen upon isolation from the molecule are identical, superimposable mirror images, and thus hydrogen atoms are homomorphic atoms, and methyl groups similarly are identical, and upon isolation they are superimposable mirror images to each other. Thereby methyl groups are homomorphic groups in this molecule. Though they are identical, there will be difference in their constitutional, geometrical or stereochemical relationship between these ligands. The study of this constitutional, geometrical or stereochemical relationship between homomorphic ligands is known as topicity. Topicity is the geometrical or stereochemical relationship between these types of homomorphic groups or ligands or atoms and the concerned structure of the molecule. Different types of relationship are possible for a homomorphic ligands or group or atom. This relationship can be referred to as homotopic and heterotopic. Ligands cannot by itself be called homotopic or heterotopic. In order to use these terminologies, a comparison with other homomorphic ligands or ligands present either in the same molecule or in different molecule is necessary. Usually two criteria are used to decide whether the ligands or groups are equivalent or not. The first criteria is substitution addition criteria, and the second is symmetry criteria. And these two criteria are employed to determine the topic relationship of homomorphic ligands. Okay, let us first discuss homotopic ligands. We can examine whether the ligands are homotopic or not either by substitution or addition criteria or by symmetry criteria. Let us see the example. It is methanol. There are three hydrogen atoms in methanol. Then if you replace the first hydrogen HA by chlorine, we will get chloromethanol. And if we replace HB by chlorine, we will get another chloromethanol. And then if we replace HC by chlorine, then we will get another methanol. All these three methanols are identical. And so if we substitute these three hydrogen one by chlorine, we will get three identical products. So we can say two or more ligands that are identical when viewed in isolation, but individual replacement of these ligands by other give rise to identical molecule, then they are called homotopic ligands. Here HA, HB and HC are homotopic ligands. Okay, see another example. It is an alene. If we substitute the first hydrogen HA by chlorine atom, then we will get chloroalene. And if you replace the second hydrogen atom HB by chlorine, we will get another chloroalene. Both of these chloroalenes are identical, and hence the HA hydrogen and HB hydrogen are homotopic ligands. See, it is tartaric acid. If you replace HA hydrogen by bromine, we will get bromotartaric acid. That is 2-bromo-tartaric acid. Then if you replace the HB hydrogen by bromine, we will get another tartaric acid. You can see by turning the molecule, the first molecule 180 degree in plane, we will get the second molecule. And so these are identical products, and hence The HA hydrogen and HB hydrogens are said to be homotopic hydrogens. Okay, according to symmetry criteria, two homomorphic ligands are homotopic if they can interchange position by rotation around CN axis. For example, in the case of propane, if you rotate the molecule through the C2 axis with respect to this central carbon atom, then we'll get this propane. Both are propane or identical molecule, and hence this HA and HB are homotopic ligands. Similarly, if you rotate the 2-methyl molecule with respect to its C2 axis passing through this carbon-carbon double bond, then we'll get this 2-methyl both are identical molecule, and hence the HA and HB hydrogens are homotopic ligands. Now let us discuss what are homotopic phases. Two phases of a pi system or double bond are homotopic if addition to either of the phase gives same or identical products. See, for example, it is the top phase of the alkene and it is the bottom phase of this alkene containing this carbon-carbon double bond. Then similarly, in alkene, it is the front face of this pi bond or double bond, and it is the back face of the double bond. Similarly, in the case of carbonyl group, it is the top face of C double bond O or double bond C double bond O bond, and it is the bottom face of this C double bond O. Similarly, it is the front face of C double bond O, and it is the back face of carbon oxygen double bond. Then addition to the top face or bottom face of this alkene or front face or back face of this alkene leads to the same pair of identical molecules in both the cases, then we can say this alkene or this alkene will have homotopic phases. Similarly, if addition to carbonyl group takes place either from the top face or from the back face or from the front face or from the back face leads to identical products, then we can say these carbonyl compounds having homotopic phases. For example, if we reduce acetone with sodium borohydride, addition of hydride ion may take place from through this phase or through this phase. If the addition of hydride ion takes place through this phase, then we will get this alcohol, isopropanol or 2-propanol, or addition of the hydride ion takes place through this phase on treating with sodium borohydride, then we will get 2-propanol, the same molecule. You can see both are identical, and hence both of these phases of acetone are homotopic. Similarly, in the case of addition of bromine in ethylene, bromine may add through this top phase or through bottom phase. If bromine addition takes place through top phase, you will get this 1,2-dibromoethane, and bromine addition if take place through bottom phase, we will get the same 1,2-dibromoethane, and so we will get two identical products, and hence these two phases of ethylene are homotopic. Two phases of a pi system are homotopic if they can interchange phase, results in the same structure by rotation around C2 axis. See, for example, this molecule 2-butene, upon rotation about C2 axis, interchange in phases takes place to form the same molecule, and these two molecules are identical, and hence both are butene having homotopic phases. It is the symmetry criteria for homotopic phases. That is, the two phases of the pi system are homotopic if they can interchange phase results in the same structure by rotation around the C2 axis. Similarly, in this molecule, if you rotate the molecule in 180-degree rotation, phases gets interchanged to form the identical molecule. Because these two molecules are identical, this molecule has cyclopropanone has homotopic phases. Here the carbonyl phases of the cyclopropanone are homotopic. Okay, these heterotopic ligands may be constitutionally heterotopic or stereochemically heterotopic. Two or more ligands in a molecule that are identical to each other, but on individual replacement by another ligand give rise to two molecules that are constitutional isomer of each other. Then the original ligands are said to be constitutionally heterotopic ligands. For example, see this molecule 2-methyl 2-butanoic acid. When this methyl group is replaced by X, we will get this molecule, while the red methyl group on replacing with X, we will get this molecule. These two molecules are constitutional isomers. Here, X is attached to this carbon atom containing a hydrogen, whereas in this case, X is attached to this carbon atom containing a COH group. They are constitutional isomers. Similarly, toluene, when this hydrogen, blue hydrogen, is replaced by chlorine, we will get orthochlorotoluene, whereas this red hydrogen, on replacing with chlorine, we will get metachlorotoluene. See, orthochlorotoluene and metachlorotoluene are constitutional isomers, and hence these two hydrogens are constitutionally heterotopic ligands. In this case, these two methyl groups are constitutionally heterotopic ligands, while in this case, these two hydrogens are constitutionally heterotopic ligands, because on replacement of these ligands, we will get constitutional isomers. Okay, the next type of ligand is stereochemically heterotopic ligands. The stereochemically heterotopic ligands are of two types: the enantiotopic ligands and diastereotopic ligands. See, for example, it is propanoic acid. If you replace this red hydrogen by bromine, you will get this isomer. This isomer having S configuration for this chiral carbon atom. And if you replace this blue hydrogen by bromine, we will get to this isomer. This isomer having a chiral carbon atom having configuration R. So these two isomers are related as object and non-superimposable mirror image to each other, or enantiomers. They are enantiomers. And so we can say by replacing HA and HB by bromine atom, we will get enantiomers, and thus HA and HB are enantiotopic ligands. So when two or more ligands in a molecules that are identical, but on individual replacement by another ligand give rise to two molecules that are enantiomers or non-superimposable mirror images of each other, then the original ligands H and HB here are said to be enantiotopic ligands. See another example. It is chloroalene. When this blue hydrogen is replaced by chlorine, we will get this dichloroalene. Then if we replace HB by chlorine, we will get this dichloroalene. These dichloroalenes are enantiomers to each other. Therefore, HA and HB are enantiotopic ligands. Similarly, see this example. When the red hydrogen HA of this H2 group is replaced by chlorine, we get this molecule. It is chloropropanoic acid with the configuration of this chiral carbon atom R. Similarly, if we replace HB hydrogen of the CH2 group by chlorine, we will get this chloropropanoic acid, where the chiral carbon atom has the configuration of S, and hence these two molecules are enantiomers. Thus, the HA proton and HB protons are enantiotopic. See this example. In this case, if we replace this HA hydrogen of the CH2 group by bromine, we will get this product having configuration S for this chiral carbon atom, newly formed chiral carbon atom. And if we replace the HB hydrogen by bromine, we will get this molecule having R configuration for the newly formed chiral carbon atom. These two are enantiomers. These two molecules are enantiomers, and hence we can say the hydrogen, blue hydrogen and red hydrogen, or HA and HB hydrogen of these CH2 groups are enantiotopic ligand. Okay, now let us see what are diastereotopic ligands. See, it is chloroethene. If you replace the red hydrogen HA of this chloroethene by chlorine atom, thereby we will get this cis 1,2-dichloroethene. Then if you replace the HB hydrogen of this chloroethene by chlorine, we will get trans 1,2-dichloroethene. See, cis 1,2-dichloroethene and trans 1,2-dichloroethene are diastereomers, and hence we can say the HA hydrogen and HB hydrogen are diastereotopic. That means if the replacement of two hydrogen give two diastereomers, then the hydrogen atom are said to be diastereotopic hydrogen or diastereotopic ligand. Okay, see this molecule. It is 1,2-dichloropropane, which has a chiral center here, and this chiral carbon atom is attached with another achiral carbon atom containing these two hydrogen. If one of these hydrogen, for example HB hydrogen of this achiral carbon atom, is replaced by an achiral ligand, for example OH, this achiral carbon atom becomes chiral. Thereby we will get 1,2-dichloropropanool. Similarly, if we replace this blue hydrogen from the achiral carbon atom that is attached directly with the chiral carbon atom already present in the molecule with an achiral ligand OH, then we will get 1,2-dichloropropanool, and this 1,2-dichloropropanool and this 1,2-dichloropropanool are related as diastereomers. Then the HA hydrogen and the HB hydrogens are referred to as diastereotopic hydrogen. Okay, here you can see the molecule already has a chiral center. That chiral center is attached to this carbon atom containing, or this carbon atom, achiral carbon atom containing the ligand that has to be replaced. And if we replace these ligands with an achiral ligand, we will get diastereomers. Thus, these ligands here, HA hydrogen and HB hydrogen, are called diastereotopic hydrogen or diastereotopic ligand. In the case of cyclic compound, for example, this molecule, see it is chlorocyclobutane. If you replace this hydrogen, HA hydrogen, by an achiral ligand, OH, thereby we will get this molecule. This chlorine and OH groups are trans to each other. And if you replace the HB hydrogen from this chlorocyclobutane with OH group, then we will get this chlorocyclobutanol, but it is cis. This chlorine and OH are in cis orientation. Thereby we will get, by replacing HA and HB, we will get trans and cis chlorocyclobutanol, the diastereomers, and hence HA hydrogen and HB hydrogen are diastereotopic ligand. Okay, so we have already discussed homotopic ligands, enantiotopic ligands, and diastereotopic ligand. Now let us consider homotopic phases, enantiotopic phases, and diastereotopic phases. Okay, first let us consider homotopic phases. See, in the case of a carbonyl compound, it is aceton having a C double bond O, or it is a pi system. If this aceton is treated with HCl, addition reaction takes place to form corresponding cyanohydrine. This cyano group may attack from top face or maybe from bottom face. If cyano group attack the aceton from top face, then we will get this cyanohydrine. And if cyano group attacks from the bottom face, then we will get this cyanohydrine. Both of these cyanohydrines are identical. You can see both are identical. And hence we can say acetone molecule has homotopic phases. So if a molecule containing a pi system has homotopic phases, then addition reaction leads to the formation of homomers or identical structures. Okay. Similarly, cis-2-butene has homotopic phases. For example, if cis-2-butene is treated with a parasitic acid, for example, if the epoxidation takes place from top phase, then we'll get this epoxide. Then if the epoxidation takes place from the bottom phase, then we'll get this epoxide. These two epoxides are identical or homomers, and hence we can say cis-2-butene has homotopic phases. Okay, now let us see what are enantiotopic phases. You know, the two phases of a pi system or double bond are enantiotopic if addition to either phase give enantiomeric products. See, for example, benzaldehyde on treating with the methyl magnesium bromide, a Grignard's reagent. The addition of this Grignard's reagent may take place through the top phase or through the bottom phase. If the addition takes place through the top phase, then we will get this alcohol. This newly formed chiral center has configuration R. Then if the Grignard's reagent, the addition of Grignard's reagent takes place through the bottom phase, then you will get this alcohol having configuration S for the newly formed chiral center. And so these two are enantiomers. These two molecules are enantiomers. Thus, we can say benzaldehyde has enantiomeric or enantiotopic phases. The two phases of benzaldehyde, carbonyl group of the benzaldehyde, are enantiotopic. Okay. Similarly, if you add hydrogen cyanide to benzaldehyde, we will get corresponding cyanohydrine. If the addition of hydrogen cyanide takes place through the top phase, then you will get this cyanohydrine having configuration S for the newly formed chiral center. And if the addition of hydrogen cyanide takes place through the bottom phase, then the newly formed chiral center having configuration R. Thus, we can say these two cyanohydrines are related as enantiomers, and hence we can say the benzaldehyde having enantiotopic phases for the carbonyl group. Okay, similarly, the epoxidation of trans-2-butene by peracetic acid forming two isomers, they are enantiomers. The relationship is enantiomeric, and hence we can say the trans-2-butene has enantiotopic phases. Epoxidation on through the top phase of this trans-2-butene leads to the formation of this isomer, and epoxidation of trans-2-butene by this peracetic acid through the bottom phase, this isomer is obtained, and these two isomers are enantiomers, and hence we can say trans-2-butene has enantiotopic phase. Then let us see what are diastereotopic phases. We had seen diastereotopic ligands are ligands attached to a carbon atom adjacent to a stereo center. Similarly, in the case of diastereotopic phases, the two phases of the carbonyl group or a pi system are adjacent to a stereo center. See, for example, this molecule here if hydrogen cyanide addition takes place through the top face of this carbonyl group, then we will get this isomer. A new chiral center is created, and this new chiral carbon atom having S configuration. Then if hydrogen cyanide is added through the bottom face, we will get this isomer. The new chiral center will get the configuration of R. So these two isomers are diastereotopic. They are diastereotopic, and hence we can say this molecule has diastereotopic phases in the carbonyl group. Okay, then see this example. Here this carbonyl group is attached to this stereo center. Then the carbonyl group having two phases. If it is reduced by lithium aluminum hydride, and then hydrolysis. If the addition of hydride ion takes place through the top phase, then we will get this secondary alcohol. And if the hydride addition takes place through the bottom phase, then 3-chlorobutane 2-on give this secondary alcohol. See, these two secondary alcohols are diastereomers, and hence we can say 3-chlorobutane 2-on having diastereotopic phases. Okay, now let us discuss prostereoisomerism or prochirality. You know, molecules having stereoheterotopic ligands, for example, enantiotopic ligands, exhibit prostereoisomerism or prochirality. Prochiral molecules are those which are achiral, can be converted into chiral molecule by substitution in a single step. That means prochirality may be the result of substitution of sp3 carbon, usually hydrogen, with other substituent, results in chiral center. Or prochirality may be the result of addition reaction of an sp2 carbon to a chiral sp3 carbon with a nucleophile. For example, see this molecule having this CH2 group with these two hydrogen. When one of the hydrogen, say for example this HA hydrogen, is replaced by chlorine, the achiral carbon atom becomes chiral. This carbon becomes a chiral center and its configuration is R. If you substitute HB hydrogen by chlorine, we will get this molecule having this chiral center. It has S configuration. Both are enantiomers, and hence, as we discussed earlier, these two hydrogens are enantiotopic. But see, a new chiral center is created from the achiral carbon atom, and so this achiral carbon atom in this molecule is prochiral, and these hydrogen atoms are prochiral hydrogen atoms. For example, this red hydrogen, HA hydrogen, on substitution we get a molecule with the R configuration, and hence this HA hydrogen may also be referred to as pro-R hydrogen. Similarly, HB hydrogen upon substitution, we get a chiral molecule with the S configuration. Thus, the HB hydrogen may refer to as pro-S hydrogen. This concept is called prostereoisomerism or prochirality. Okay. Similarly, prochirality may also be the result of addition reaction of an sp2 carbon. See, for example, 2-butanol. 2-butanol has this carbonyl group having prochiral center. This sp2 carbon is prochiral because upon reduction with the sodium borohydride, we will get two enantiomers. On top phase addition, we will get this enantiomer, R enantiomer, and with the bottom phase addition of hydrogen to this carbonyl group lead to the formation of this S enantiomer. Thus, even though this carbon, sp2 carbon, is not chiral or it is achiral, it is prochiral. It is the concept of prochirality or prostereoisomerism. So we had already discussed the topicity or stereotopicity in detail. Among the topicity, we had already discussed the enantiotopic ligand and phases, diastereotopic ligands and phases, homotopic ligand and homotopic phases, and then we had also discussed the pro-stereoisomerism or pro-chirality of molecules. I think you might have got a clear idea about these concepts. I hereby conclude this video. Thank you for watching. Thank you.